So I'll be giving an overview presentation of the Geohazard Supersites and Natural Laboratories, GSNL. So GSNL is essentially a geo initiative. It was established in 2010. And the main aim of GSNL is to really improve our monitoring and research on both seismic and volcanic hazards. So we're doing this by facilitating access to both satellite data and ground-based data. And this is in our key high-risk areas. So these are referred to as our geohazard super sites. And of course, another main reason for doing this is to actually ensure that these new results and information from the super sites feed directly to our key stakeholders, so such as civil protection agencies, and then actually inform decision-making processes. Okay, so this is can you see the full slide here, or is it impaired by the screen? It's okay? Yes. Okay, so this is a map showing the location of the different super sites and also the one natural laboratory. So at present there are 10 volcano super sites shown here and 2 earthquake or fault super sites. And then in addition to that, there's one natural laboratory, which is the San Andreas Fault. Okay, so the main EO products here are satellite images. So these are free satellite images that are obtained every year by the super sites. And in this table, you can see a list of the super sites and then also the different types of satellite data. So for example, the super sites obtain a set quota for Cosmo Sky images every year. So this is from the Italian Space Agency, TerraSAR-X from the German Space Agency, SAOCOM, and also Pleiades data. So the first three here are typically used for generation of interferograms. So these are, if you like, deformation maps produced in our key area. So for example, they may be showing deformation at active volcanoes. But the Pleiades data, I mean, this is an optical satellite data, and it's typically used to generate digital elevation models, for example, over our areas of interest. And it's also highly used during volcanic crises or earthquakes. And this is to map, for example, during a volcanic eruption, it could be mapping different hazards such as pyroclastic flow deposits or lava flows, for example. Okay, so the intended impact of GSNL and the supersites is firstly to empower the scientific community with providing a wealth of open access data. And this, of course, is then informing seismic, or I should say, scientific studies. So to increase our general knowledge, let's say in this example about, changes in volcanic activity or seismic activity or specific hazards. So to really improve our understanding of geohazards. But on top of that, and certainly in the recent years and going into the future, I think there's been a lot more emphasis on the rapid uptake of this information from the super sites to key stakeholders such as civil protection. As I say, to make sure that the information coming from the super sites is given to key stakeholders in a timely manner to help inform decision-making processes. Okay, so this slide here is essentially showing the key users and partners of GSNL. So on the top here, we have the supersite coordinators. So this is for the various volcano and seismic supersites. Of course, also the in situ data providers, and then the satellite data providers, which I showed briefly on the previous slide. So, of course, in addition to this, we also have a multitude of scientists working around the world using this supersite data. Now, this currently is approximately more than 150 scientists around the world working with supersite data. So now I'm just going to go through a few examples from the different supersites shown here. So first we have the Hawaii supersite. Now this is a very well-established supersite, and here we're looking at really quite an innovative technique that they're using to map tephra deposits related to the recent eruptions that are occurring at Kilauea. So essentially, since the end of 2024, so about a year ago, there've been a series of these highly episodic lava fountaining events. And during these events, essentially, there's been 37 now since December last year. And during these events, there's a large increase in SO2 emissions and also tephra or ash fallout. And in this example, the Supersites scientists have been mapping the ash fallout, and it's displayed in the green amplitudes you can see here. Now, this has been particularly challenging for the scientists here and especially scientists at the Hawaiian Volcano Observatory because the ash fallout has been affecting roads. So they have been clearing the ash from the roads and also having to dig out some of the monitoring equipment. But despite these challenges, Hawaii is a great example where essentially the supersite data has been completely integrated into their operational monitoring. So this enables them to inform civil protection and other stakeholders such as landowners in the area, during these events. So moving on now to the Icelandic volcano supersite. So there has been a lot of activity here in on the Reykjanes Peninsula, which is on essentially the southwest tip of Iceland. Activity here recommenced at the end of 2019, excuse me, with the first eruptions in Fagradalsfjall in 2021 to 2023. There were three eruptions in this area, and then activity jumped in December 2023 to the Svartsengi volcanic field. And essentially, excuse me, this area is very close to the town of Grindavik, important infrastructure such as a power plant, and also a very popular tourist destination called the Blue Lagoon. So this slide is just showing an example of how the supersite data is used. So here, during these episodes within the Svartsengi volcanic system, excuse me, we have continued inflation of the reservoir prior to these diking events and eruptions. So on the left-hand side, we're looking at Cosmos SkyMed data showing this inflation. And on the right-hand side, we've got a series of different interferograms and predominantly ISI. Now, these are used to map the deformation during the actual diking events and eruptions. And this is because these are very short period interferograms. And this is important to use during these events because typically these last on the order of hours. And straight after, the volcano reservoir starts to inflate again, which is why it's more useful during the events to use the short period interferograms. But I'll come back to that a bit later. So here's an example again. On the left-hand side, we're looking at a series of lava flows that have occurred essentially since December 2023. This is the location of the town of Grindavik here. And what we're doing is we're using this data, the supersite data in real time to essentially map volume changes within the Svartsengi reservoir in between these different diking events. And this is feeding directly now into the medium-term eruption forecasting. It is still challenging because these events are occurring quite frequently. So as I say, since December 2023, we've now had 9 eruptions in this area. It becomes more difficult also if there's a change within the volcanic system. So during the first few events shown here, we were calculating the volume drop in the reservoir during the prior event and assuming that this volume had to be recharged before the next event was triggered. Now, this was working very well for the first few series of eruptions, so essentially up until March 2024. But then, as you can see, something in the system changed, and after this, a larger volume of magma seemed to be required to accumulate before the next event was triggered. This, of course, then provides a longer uncertainty period, if you like, or time window for the forecast. Of course, now we are also coming up to the festive season, Christmas. Many people want to return to their homes in Grindavik over this time of year, which of course makes things more challenging. Okay, this is just an example of where one of the super sites was actually asked for assistance during a seismic unrest. And this was at Santorini earlier this year, in January this year, where there was a major volcanotectonic unrest initiated about 10 kilometers northeast of the island of Santorini. So here's the island of Santorini on this upper panel on the left-hand side, you can see here. And this is where the extreme seismic activity was occurring in January this year. So scientists from the Iceland supersite provided support by modeling the deformation data and helping to determine the cause of unrest. So here the modeling results indicated that this was in fact triggered by a massive dike intrusion just to the southeast of Colombo volcano, which is shown here. Okay, moving on to the Virunga supersite. Now, this supersite faces very difficult challenges, and this is partly because of the ongoing conflict in the region, but also because of its close proximity to a very dangerous volcano. So this is Niragongo volcano, which is about 12 kilometers to the north of the city of Goma. Now, just to give you a better understanding of kind of the potential for societal impacts here, during the activity here in 2021, there was a large dike intrusion and an eruption which lasted several weeks. And during this period, approximately 400,000 people were evacuated from Goma, and about 3,600 houses were destroyed by lava flows during this event. In comparison, for the recent activity in Iceland that I was just showing you, on the 10th of November 2023, when there was a large dike intrusion under Grindavik, about 3,300 people were evacuated, and in January 2024, 3 houses were destroyed by lava flows. So I just want to give you a better understanding of why this super site really needs additional support, and this is support both based on funding, new infrastructure, but also training as well of local scientists. Okay, moving on to the sustainability. So GeoGSNL, I mean, it is mainly based on in-kind resources. So these are, for example, contributed salaries by staff, data that's made available, obviously from the satellite agencies, but also infrastructure as well from the different agencies involved in the super site. So we do try to obtain direct funding through other project calls, for example, other project proposals or international projects. And perhaps this may fund, for example, field work or some equipment that's used by the super sites. But of course, donor funding is still sought for super sites in less developed countries, such as the Virunga super site. So moving forward, our future strategies are to really encourage more collaboration and data sharing between the existing super sites. These super sites face different challenges, and of course, they have different areas of expertise as well. So, depending on, for example, the different styles of eruptions that are occurring in the different areas. So, we feel that enhanced collaboration here is extremely important. Also, as I mentioned, to provide additional support to super sites within less developed countries, such as the Virunga super site. I mean, I think it is extremely important to support, these super sites and countries that obviously have extensive geohazards, but don't have the same opportunities or funding that's available to other super sites, for example. We'd also like to engage with private satellite companies such as ICEYE, and this is in order to obtain these shorter period interferograms that I was showing you are extremely useful in Iceland for these short-lived diking events. Possible for Geo to assist GSNL with these future objectives? And if so, how would you propose going forward to achieve this? Thank you.